down. And I'll know it's cold enough once the liquid nitrogen stops boiling, because that means the thing inside it is the same temperature as the nitrogen. If you had like marshmallows or something.
Forgot my apple.
Yeah. Okay, so I'm gonna wait just a little bit longer because this is still boiling. One thing to note is that I'm not doing this cool down thing at an arbitrary place on the table. I'm doing it right here. So this has a little label next to it. This is the pinning station. So one of the things that happens, oh, this is off.
Oh, we can turn back on.
Yeah, I have a slide that kind of talks about it a little bit. Is it's important to say, where you cool it down? Oh, no. Ah, there we go. Okay. I'm gonna wait for this to come back up before I do this. As long as I haven't done this, you're still paying attention to me. Okay. So this is one of my hidden slides. So this goes into a little bit more detail about the difference between these type 1 and type 2 superconductors. So the key feature about these things is that for type 1s, if you do a diagram of, I'm going to apply some magnetic field to this superconductor, and this is saying at what temperature in that field is it still a superconductor. So you can see that for a given temperature, as you apply a stronger and stronger magnetic field, it stays being a superconductor, but at some point the magnetic field breaks that state. It collapses it down to a normal metal. And that happens instantaneously. It goes from superconductor, all of it superconductor, to all of it being normal immediately. That's something that all type 1s do. Type 2s are a little more complicated. Type 2s go through an intermediate state where it's fully superconducting, but then there's a lower critical field where it becomes this more complicated mixture of normal state and superconducting state coexisting with each other. And then if you go to really high magnetic fields, you can also break that state. What I'm doing now is the magnetic field here has been tuned so it's somewhere in between here, somewhere in that coexistent state. So now, I'm going to try this. And on the next slide, I'll show you why this happens. I'm going to take this out.
Ooh.
On here. So if you want to come up, you can see this. This is levitating. And a really cool thing is that a lot of people, you know, kids are always impressed by this, but some people, especially scientifically oriented people, are like, oh, it just floats. Like lots of things float. Magnets float all the time. That's fine.
Right.
That's true. But what they don't do is you could not tilt this and put it anywhere in space. If I had a better sample and I was braver, you could flip the whole thing upside down and it would stay there in that locked position. So this is a phenomenon called vortex spinning. And on the next slide, I can explain that, or gesture at why this happens. So this is a little bit more detailed picture of that transition I was talking about for type 2s. So down here, it's fully superconducting. And when something is fully superconducting, it enters something called the Meissner state. Now that's just a technical way of saying if you try and put any magnetic field through that material, it fully expels it. It acts like a perfect diamagnet. It's not quite the same thing as perfect diamagnetism, but effectively it looks like it is. And so it just doesn't let magnetic field go into it. In the mixed state, now you have some superconductivity, but also some normal states. And when that happens, some of the flux lines from the magnetic field actually can go through the material. Now the key thing then is that there are impurities in the material. And those impurities lock down some of these magnetic field lines. This is a thing called vortex pinning. It's very much about these vortices over here. These vortices get locked in place, and those vortices actually lock the rest of the material in place too.